Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss shell end tube heat exchangers and heat transfer fouling resistance. After distillation, heat transfer is the most important operation in a process plant. Most of the heat transfer in chemical plants and petroleum refineries takes place in shell end tube heat exchangers. The surface condenser we discussed in previous lecture is an example of a shell end tube heat exchanger. A wide variety of heat exchangers are available, some of which you may have seen like plate, spiral, and coil, to name just three. But 99% of the heat exchangers I have worked with are ordinary shell end tube exchangers, the design of which has not changed since the 1920s. Before considering the process aspects of heat transfer, let's look at the mechanical components of the heat exchanger shown in picture. This shell end tube heat exchanger is actually a compromise between four aspects of heat exchanger design. Allowance for thermal expansion, efficient heat transfer, ease of cleaning, mechanical robustness. Allowing for thermal expansion. Referring to picture, we can see how a floating head exchanger works. The tube side flow enters the bottom of the channel head. This assumes the cold fluid to be on the tube side. The cold fluid may be on the shell side or the tube side of an exchanger. The convention is to put the cold fluid nozzle on the bottom of the exchanger. Sometimes this is necessary. Sometimes it does not matter, but it is still the convention. Inside the exchanger's channel head, we have the pass partition baffle, which divides the channel head into two equal portions. This baffle forces the total flow only through the bottom half of the tubes. The tubes themselves are pipes of either 0.75 or 1 inch OD, outside diameter. The front end of each tube is slipped into a slightly larger hole drilled into the channel head tube sheet. This tube sheet is a disc about 2 inch thick, slightly larger than the inner diameter of the shell ID. The tubes are firmly attached to the tube sheet by rolling. After a tube is pushed into the tube sheet, a tapered tool is inserted into the open end of the tube and forcefully rotated. The tube's diameter is thus slightly expanded. While rolling is quite effective in sealing the tube inside the tube sheet, rolls have been known to leak. The tube side fluid now flows into the floating head, which acts as a return header for the tubes. The tube side flow makes a 180 degrees turn and flows back through the top half of the floating head tube sheet. The floating head is firmly attached to the floating head tube sheet. But why is it that one end of the tubes must be left free to float? The reason is thermal expansion, or, more precisely, the differential rate of thermal expansion between the tubes and the shell. Not all shell and tube exchangers have a floating head. Many exchangers have individual U-bends for each tube. In such cases, each of the U-bends functions like a mini floating head for each tube. The requirement to leave one end of the tubes free to float creates a rather unpleasant process problem. The most efficient way to transfer heat between two fluids is to have true countercurrent flow. For a shell end tube exchanger, this means that the shell side fluid and the tube side fluid must flow through the exchanger in opposite directions. When calculating the log mean temperature driving force, LMTD, an engineer assumes true countercurrent flow between the hot fluid and the cold fluid. But this is not the case with a floating head exchanger. The tube side fluid reverses direction in the floating head. It has to. There is no way to attach the tube side outlet nozzle to the floating head. It is a mechanical impossibility. So, we bring the tube side fluid back to the top half of the channel head. Half of the tubes are in countercurrent flow with the shell side flow. And that is good. But the other half of the tubes are in concurrent flow with the shell side flow. And that is bad. When calculating the LMTD for such a floating head exchanger, the engineer has to apply the F-factor derating coefficient to reflect the loss in heat transfer efficiency because of the floating head. A typical exchanger might lose 5 to 30% of its capacity because of non-true countercurrent flow. 1-pass tube side exchangers. I have not been completely accurate in the preceding discussion. Many exchangers are designed to bring the tube side fluid in one end of the shell and out the other side. This is a true countercurrent arrangement. To provide for thermal expansion in such exchangers, an expansion joint is provided. These expansion joints are prone to leaking. They represent inferior mechanical engineering practice. For moderate temperature and low pressure condensers, such as vacuum surface condensers, a single pass on the tube side is not uncommon. These exchangers are typically fixed tube sheet designs. Such exchangers are fine from a purely process point of view. However, there is no practical way to disassemble the exchanger to clean the outside of the tubes, that is, the shell side. This inability to clean the shell side frequently leads to tremendous loss of efficiency after the condensers foul. Shell side flow. The hot shell side flow enters the exchanger, as shown in picture, through the top inlet nozzle. Not shown on this sketch is the impingement plate, which is simply a square piece of metal somewhat larger than the inlet nozzle. Its function is to protect the tubes from the erosive velocity of the shell side feed. The plate lies across the upper row of tubes. The 4 tube support baffles shown in this exchanger as shown in picture serve a dual function. They serve to support the tubes. More importantly, they promote high crossflow velocity. The concept of crossflow velocity is quite important in understanding how heat exchangers work. This concept is related to a flow phenomenon called vortex shedding. Perhaps you have seen a wire quivering in the wind. What causes the wire to vibrate with such energy? What causes water to swirl around a tree stump in a river? When a fluid such as air or water flows perpendicularly across a wire or tube, vortices, such as those shown in picture, are created. The resulting turbulence that forms behind a wire will cause the wire to vibrate. The turbulence that forms behind a tube in a heat exchanger promotes good heat transfer. Turbulence always encourages good sensible heat transfer. The greater the velocity, the more violent the turbulence. For example, I recall a -40 degrees Fahrenheit day. The air is quite still, and I am comfortable. Suddenly the wind comes up. The rate of sensible heat transfer from my body to the ambient air increases tenfold. Why does this happen? Our bodies are always surrounded by a thin layer or film of stagnant air. This film is like a layer of insulation. It retards heat transfer between our skin and any surrounding fluid. Movement of the fluid causes turbulence. The turbulence disturbs the film and reduces the film's resistance to heat transfer. To encourage vortex shedding and turbulence on the shell side of a heat exchanger, we must increase the crossflow velocity. To calculate the crossflow velocity, we proceed as follows. 1. Find the distance between the adjacent tube support baffles in inches. 2. Count the number of tubes at the edge of the tube support baffle. As shown in picture, this would be 7. 3. Multiply the number of tubes by the space between each tube in inches. 4. Multiply the inches measured in step 1 by the inches calculated in step 3. 5. Divide by 144 to obtain the shell side crossflow area in square feet. 6. Divide the pounds per second of shell side flow by the fluid density in pounds per cubic foot. This will give you the volumetric flow in cubic feet per second. 7. Divide the volume calculated in step 6 by the area calculated in step 5. This is the crossflow velocity. A good crossflow velocity for water is 3 to 5 feet per second. For fluids other than water, a reasonable crossflow velocity, in feet per second, is 30 divided by square root of density, where the density term is the density of the shell side fluid, in pounds per cubic foot. The baffle cut, shown in picture, is usually about 20 to 30% of the diameter of the baffle. The smaller the baffle cut, the more perpendicular the flow across the tubes. Perpendicular flow encourages desirable crossflow velocity and vortex shedding. But a smaller baffle cut will also increase the pressure drop on the shell side. Effective shell side pressure drop. Reducing the baffle spacing increases cross-flow velocity and improves heat transfer. But it also increases the shell side pressure drop. Reducing the baffle cut also improves heat transfer but increases delta P. Too much shell side pressure drop can create a problem. The problem is flow through the bypass area shown in picture. This bypass area is caused by three factors. The tube support baffles must have a diameter somewhat smaller than the ID of the shell. The holes drilled in the baffles for the tubes cannot be drilled too close to the edge of the baffles. The use of an impingement plate requires the removal of several rows of tubes. This creates a large gap between the edge of the tube bundle and the shell. It is the primary purpose of the seal strips to reduce this gap. For the seal strips to fulfill this function, one of the seal strips in each pair must extend the full length of the tube bundle. This is rather complicated to explain. However, if you will look at a tube bundle that has been extracted from its shell, you will understand why this is needed, and how impingement plates render seal strips essential for good sensible heat transfer from a shell-side fluid. The gap thus created between the shell ID and the outer row of tubes will permit the shell-side fluid to bypass around the tubes. This is obviously very bad for heat transfer. And as the shell-side delta P increases, the percent of fluid that is squeezed through the bypass area increases. If the baffle spacing gets too small, the shell-side heat transfer rate will actually worsen. This happens even though the cross-flow velocity increases. What can be done to correct this problem? Shell-side seal strips. See if you cannot find an old tube bundle lying around your plant. Many such bundles have pairs of metal strips set around the edge of the tube bundle. These metal strips are typically 0.25 inch thick and 4 inch wide. They extend down the length of the tubes. As shown in picture, they are inserted in grooves cut in the tube support baffles. These seal strips often increase heat transfer efficiency by 5 to 10%. The function of seal strips is to interfere with, and hence reduce, the fluid flow through the bypass area. Often, one pair of seal strips is used for every 18 inch of shell ID or inner diameter. These seal strips encourage good shell-side cross-flow velocity and also help reduce localized fouling caused by low velocity. Please note that the tube support baffles are normally installed with the baffle cut in a vertical position. I have shown the baffle cut in picture in a horizontal position for clarity. Baffles are installed vertically in most exchangers to reduce buildup of sludges in the bottom of the shell and avoid trapping vapors in the top of the shell. For exchangers with vertically cut baffles, the shell side impingement plate will be opposite the shell side inlet nozzle. Contrary to the location of the seal strips shown in picture, the critical seal strips will be set on either side of the impingement plate shown in picture. Additional pairs of seal strips can also be installed as shown in picture. Terminal tube velocity. Have you ever seen a heat exchanger tube bundle pulled? Perhaps many of the tubes were bent and twisted like partly cooked spaghetti. This distortion could not be very good for the shell side heat transfer. The cause of the bent tubes is called terminal tube velocity. Let me explain. Let's assume we have a new heat exchanger. The fluid on the tube side is crude oil. Crude oil, like many processed fluids, will eventually foul and plug heat exchanger tubes. The tendency to lay down fouling deposits is accelerated by low velocity, high temperature, dirt, salts, corrosion products, and other particulates. The crude oil is being heated by a hot oil stream circulating through the exchanger's shell. Even though the exchanger is new, the flow of crude through all the tubes is not equal. Some of the tubes naturally run somewhat slower, and in some of the tubes, heating the crude oil will run faster. Those tubes that start running slower tend to get hotter. As the crude oil in these tubes gets hotter, the growth of fouling deposits accelerates. As the buildup of deposits in the slower tubes increases, the flow through these tubes is further restricted. The lower velocity increases fouling rates and restricts flow. This also increases the temperature of the slower tubes and accelerates the rate of fouling. These tubes continue to plug and foul and run slower until crude oil flow is essentially lost. Meanwhile, the flow of crude oil through those tubes that started out running faster increases. The crude oil flow is backed out of the slower tubes by the fouling deposits. The extra flow increases the velocity in the tubes that initially ran faster. The higher velocities retard the buildup of fouling deposits. Also, the greater flow keeps these tubes cooler. This also discourages the accumulation of deposits inside the tubes. To summarize, some of the tubes in the bundle continue to foul until they plug off. These tubes get hotter until they reach the temperature of the hot oil circulating through the shell. Other tubes continue to receive more and more flow. The velocity in these tubes increases to the point where the rate of fouling becomes inconsequential. This velocity is called the terminal tube velocity. These tubes may run 50 to 150 degrees Fahrenheit cooler than the plugged tubes. Differential rates of thermal expansion. It is quite true that the floating head permits differential rates of thermal expansion between the shell and tube bundle of an exchanger. However, the floating head cannot permit differential rates of thermal expansion between individual tubes. The hotter, fouled tubes must grow. But their horizontal expansion is constrained by the cleaner, colder tubes. Since the colder tubes do not allow the hotter tubes to grow, the hot tubes bend. This, then, is the origin of the twisted tubes we see when an improperly designed tube bundle is pulled from its shell during a turnaround. The tendency to foul tubes might be eliminated by removal of salts, wax, particulates, corrosion products, polymers, free radicals, and all the myriad of other factors that contribute to fouling. Possibly, but not likely. The temperature extremes of a process may occasionally be moderated. For example, we superheat steam to an amine regenerator reboiler to slow degradation and fouling with the heat-sensitive amine. We avoid heating diethylene glycol above 360 degrees Fahrenheit to minimize fouling in our glycol dehydration unit water strippers. But in general, our latitude to manipulate process temperatures is very limited. On the other hand, we can, during the design of an exchanger, select a high velocity to combat fouling. For example, let's consider this picture. This is data from an exchanger that was designed to operate with a low tube side velocity. Note how there is a rapid loss in the heat transfer coefficient as the tubes foul and plug as a result of low velocity. The loss in heat transfer coefficient U stops only when the terminal tube velocity is reached in the unplugged tubes. Note, also, how there is a rapid increase in the pressure drop in the tube bundle as the tubes foul and plug because of the low velocity. The increase in delta P stops only when the terminal tube velocity is reached in the unplugged tubes. It would seem that it might be best to design exchangers for initially high velocity and high pressure drops. It would seem that in practice, if we were to design exchangers for a low delta P, after a few months fouling would cause a high delta P anyway. This line of reasoning is valid for both the tube and shell sides of a heat exchanger. No fooling, no fouling. This is the title of an important article published many years ago. The substance of this famous article was simple. When designing heat exchangers, use the available pressure drop to maintain high velocities through the heat exchanger equipment. Do not use safety factors in allowing for future pressure drop due to fouling. Use of such safety factors will force the mechanical engineer who designs the exchanger to use lower velocities in the design. Then the feared fouling will occur, and the delta P safety factor will be consumed. But suppose we are operating a heat exchanger subject to rapid rates of initial fouling. The start of run heat transfer coefficient U is 120 BTU per hour square feet degree F. 4 months later, the U value has lined out at 38. The calculated clean tube side velocity is 1.5 feet per second. This is too low, but what can be done? Multi-pass exchangers. It is possible to convert the 2-pass tube bundle shown in picture to the 4-pass tube bundle shown in this picture. This conversion is effected as follows. 1. The center channel head pass partition baffle is cut out. 2. Two off-center channel head pass partition baffles are welded in place, so that 25% of the tubes are above the upper baffle and 25% of the tubes are below the lower baffle. 3. Both the channel head cover and the channel head tube sheet shown in picture must be remachined to accommodate the new baffles. For a new center pass partition baffle is welded in the floating head. The floating head tube sheet must also be remachined. The resulting 4-pass tube bundle will have a tube side velocity twice as high as it did when it was a 2-pass exchanger, 3 feet per second. Experience has shown that in many services, doubling this velocity may reduce fouling rates by an order of magnitude. That is fine. But what about pressure drop? When we convert a tube bundle from 2 to 4 passes, the pressure drop increases by a factor of 8. For example, assume that the 2-pass delta P was 5 psig. With the same flow, the 4-pass delta P would be 40 psig. Let me explain. Pressure drop increases with the square of velocity. If the velocity doubles, the pressure drop would go up by a factor of 4. Pressure drop increases directly or linearly with the length that the flow traverses. The fluid must go twice as far in a 4-pass as in a 2-pass tube bundle. 4 times 2 equals 8. Quite likely, even after several years of operation, the pressure drop of a 4-pass exchanger will be greater than the delta P of a 2-pass exchanger in the same service. Quite likely, the initial U value of a 4-pass exchanger, days after it has been returned to service, will be only slightly higher than the U value of a 2-pass exchanger. However, the 4-pass exchanger will maintain its U value with time, far better than will the lower velocity 2-pass tube bundle heat exchanger. The 8-fold increase in pressure drop is certainly a stiff price to pay for this improvement in the long-term U value. But remember this, it is the clean delta P of the tube bundle that will increase by a factor of 8. Let's say that the tube side of an exchanger is currently operating, after 2 years of service, in a badly fouled state. Its delta P, as measured in the field, is 20 psig. The calculated delta P for clean tubes is 5 psig in a 2-pass configuration, or 40 psig in a 4-pass configuration. After 2 years of operation, I would expect the exchanger in the 4-pass configuration to have a delta P of 50 to 60 psig, rather than 160 psig. Why? Well, because the doubling of the tube side velocity has promoted turbulence, which retards the accumulation of fouling deposits. Of course, this is exactly the reason why we exercise. The increased flow of blood through our arteries prevents plaque from sticking to the walls of our blood vessels. The plaque, a fatty deposit derived from cholesterol, restricts the flow of blood, which causes high blood pressure and eventually strokes. Erosive tube-side liquid velocities. Tube-side fouling and plugging is greatly reduced by high velocity. For clean cooling water, a velocity of over 3 feet per second is good. For heavy crude oil contaminated with sediments and salts, a minimum velocity is about 6 feet per second. For cracking unit slurry oil contaminated with catalyst fines, a velocity of less than 5 feet per second will promote tube plugging with catalyst. The delta P varies with velocity squared. So, there is often a practical upper limit on higher velocities. But, putting aside such hydraulic limitations, there is also a practical limit regarding maximum velocities as limited by tube-side erosion. When I worked for an oil refinery, our limit for liquids was 10 feet per second. Recently, working with a very experienced process design contractor, their limit was 14 feet per second. My own design criterion has always been 12 feet per second. I have worked in plants where I found 12-inch carbon steel piping, with piping velocities in corrosive surfaces of 14 feet per second to cause erosive piping failures. For rich amine flow with particulate contamination, piping failures with velocities above 8 feet per second have occurred on units I've worked on. In summary, for surfaces with moderate corrosion potential, I would keep tube side velocities below 12 feet per second, and perhaps a bit lower for U-tube type exchangers. Shell side versus tube side. We can have any even number of tube side passes, 2, 4, 6, 8, and so on. But this certainly limits our flexibility to optimize the tube side velocity. The shell side crossflow velocity may be altered in much smaller increments by changing the tube support baffle spacing. This is one advantage of placing the fluid with the poorer heat transfer properties on the shell side. But there is another, far more critical advantage in placing the fluid with the poorer heat transfer properties on the shell side. Laminar flow. Think about water flowing slowly in a channel. Will the water in the center of the channel flow faster or slower than the water along the sides of the channel? Experience teaches that water in the center of a channel will flow faster than along the sides of the channel. Moreover, if the water flow is really slow, the water creeping along the side of the channel will barely mix with the bulk of the water flowing in the center of the channel. This is called laminar flow. Fluids in laminar flow transfer heat very poorly. The slow-moving fluid creeping along the heat transfer surface does not particularly mix with the bulk of the fluid. While the slow-moving fluid may get hot, it does not transfer its heat very efficiently to the flow of the bulk of the fluid. This is called film resistance. Laminar flow is very bad for heat transfer. After fouling, it is the second biggest reason for low U values. Laminar flow is caused by two factors: low velocities, high viscosities. A low velocity for liquids is 2 or less than 3 feet per second. Velocities of greater than 10 or greater than 12 feet per second may cause erosion of metal surfaces and should be avoided. A low viscosity is 2 or 3 centipoise or centistokes. Tap water has a viscosity of about 1 centipoise. A viscosity of tilde operator 50 centipoise is quite high. Warm maple syrup has this sort of viscosity. The viscosity of vapors is almost always very low. When we cool a liquid off, its viscosity markedly increases. I cannot generalize, it depends on the fluid. But I can say that increasing the viscosity of a fluid from 2 to 40 centipoise could reduce the observed heat transfer efficiency, U, from 100 to 25. I know this from my experience in preheating cold, viscous, crude oil, offloaded from tankers. The best way to diminish the effect of laminar flow is to place the higher viscosity fluid on the shell side. The shell side of an exchanger is far more resistant to heat transfer loss due to film resistance than is the tube side because of the vortex shedding shown in picture, the rapid changes in direction due to the tube support baffles. Purely in terms of heat transfer, it follows that the higher viscosity fluid should be placed on the shell side. Sometimes, pressure and corrosion force the designer to allocate the higher viscosity fluid to the tube side. Also, your maintenance department would vastly prefer that the fouling fluid be placed on the tube side. Exchanger cleaning. To disassemble an exchanger may require a lot of work. However, if only the tube side has to be cleaned, the amount of labor required may be halved. Referring to picture. 1. The channel head cover is removed. 2. The bell head, or floating head cover, is dropped. 3. The floating head is removed. Each individual tube can now be cleaned by one person with a long tube and a hydroblast machine. On the other hand, cleaning the shell side requires pulling the entire bundle out of the shell. This is a massive undertaking requiring a special bundle pulling machine and a large crew of pipe fitters. Then comes the hard part, cleaning the bundle. If the deposits are soluble in a solvent, the shell may be soaked in a chemical bath. Sometimes this bath must be kept hot to dissolve the deposits at a reasonable rate. Sometimes the deposits must be attacked with a hydroblast machine. If the design engineer has selected a correct tube pitch, cleaning the shell side of an exchanger with a hydroblast machine may be a reasonable proposition. U-tube bundles. This picture shows a U-tube bundle. Cleaning the U-bend of such a bundle is quite difficult even by hydroblasting the tubes with a jet of water. My main objection to U-tube bundles is not the difficulty in cleaning, but the fact that such bundles cannot be inspected after cleaning to verify that the tubes are actually clean. In a floating head bundle as shown in picture, looking down the straight tubes with the floating head removed allows the verification that the tubes have been completely cleaned. The disadvantages of the floating head design shown in picture as compared to the U-tube design shown in picture are: cost is about 10 to 15% greater. The difficulty of getting a tight, leak-proof closure between the floating head tube sheet and the head itself. In general, process personnel prefer floating heads. The maintenance department prefers U-tube bundles. Effective cleaning of U-tube exchanger bundles. Hydroblasting U-tube bundles may or may not completely clean the tubes. However, there is a method that is certain to completely clean even a badly plugged and foul tube: pigging. Tiny pigs, that is, small brushes, are individually forced, one pig at a time, through each tube with a high-pressure water gun. One of my clients has cut open U-bends to prove the effectiveness of this pigging. It's effective but expensive. About $10,000 in 2012 for a crude preheat bundle, 300 to 400 square feet. This is a good argument for a floating head bundle rather than a U-tube bundle. There are two types of pigs used. One is a nylon brush and the other is a metal cleaner. At least in cooling water services, the metal cleaner type of pig is the more effective. Selecting proper tube pitch. From a theoretical heat exchanger perspective, the triangular tube pitch shown in picture is best. The term pitch refers to the geometry and distance between the holes drilled into the tube support baffles. A triangular pitch means the holes are drilled in the pattern of a 60 degrees equilateral triangle. For example, we might have a 0.75-inch tube, OD, on a 1-inch triangular pattern. The advantages of this tube pitch are: many tubes are squeezed into a small shell ID. The tube spacing promotes turbulence and hence good heat transfer. This all results in reduced capital cost. The disadvantage of this tube pitch is that, except for the outer few rows of tubes, the shell side cannot be cleaned by hydroblasting. Obviously, this sort of arrangement should never be used in a fouling service, unless the deposits can be chemically removed. The second example shown in picture is 0.75-inch tubes, also set on a 1-inch spacing. But this time, the arrangement is a square pattern. This pattern reduces the number of tubes in a shell of a fixed ID. Also, less turbulence is created by the tubes. Some fluid may flow between the tubes without encountering the tubes at all. All this reduces heat transfer efficiency. But hydroblasting between the tubes is usually possible depending on the extent of tube bending and twisting. The third example shown in picture is my favorite for sensible heat transfer in fouling service. This consists of 1-inch tubes set on a 1.5-inch rotated square pitch. The pitch layout is the same as that of the square pitch. It is just the tube bundle that is rotated by 45 degrees relative to the shell side flow. The shell side fluid cannot flow without interference between the tubes. Hence, the tubes promote turbulence and improve heat transfer. The large tubes, and especially the doubling of the space between the tubes, reduce the heat transfer surface area that can fit into a shell of a given ID. But the primary objective of the 1-inch tubes on a 1.5-inch rotated square pitch is that it is relatively easy to hydroblast. Note that 1-inch tubes on a 1.5-inch tube pitch are 0.5-inch apart. 1-inch tubes on a 1.25-inch tube pitch are 0.25-inch apart. The larger spacing greatly reduces the tendency for fouling deposits to bridge the gap between the tubes. Once the space between adjacent tubes is bridged over with deposits, the flow of fluid between these tubes drops to zero. The local heat transfer rate drops close to zero. Overall, shell side increment P rises as flow is diverted away from the restricted zone. Using the larger tube pitch will reduce the number of tubes in a shell by about 35%. But in a fouling service, this may greatly increase run times between cleaning and, in my experience, is a worthwhile incremental investment. 2-pass shell. Most of the heat exchangers in your plant are designed with the shell side inlet and shell side outlet at opposite ends of the shell, as shown in picture. However, you may have noted a few exchangers in which both the shell side inlet and shell side outlet are next to the channel head. This is a 2-pass shell side exchanger of the type shown in picture. The critical feature of this exchanger is the longitudinal baffle, which extends down the length of the shell. The baffle is fitted directly to, and thus becomes physically part of, the tube bundle. The function of the baffle is to force the shell side fluid to flow down the entire length of the shell and back again to the shell side outlet nozzle. Such an exchanger is truly countercurrent. The engineer does not apply the F-factor derating coefficient to the log mean temperature driving force, as would normally be used for non-true countercurrent flow. This would make it seem that the 2-pass shell configuration is inherently more efficient than the ordinary single-pass shell exchanger. And it is, in theory. Then why do we see so few of these exchangers in service? The reason illustrates the true nature of the shell and tube heat exchanger. It is a compromise between an ideal heat transfer configuration and practical mechanical limitations. In this case, the difficulty is in preventing leakage around the longitudinal baffle. Such leaks permit the shell side fluid to short-circuit the tube bundle, that is, a percentage of the inlet flow may flow directly to the outlet nozzle. In extremely serious cases, I have seen the bell head, shown in picture, 100 degrees Fahrenheit colder than the shell side outlet temperature. When new, the longitudinal baffle seal, which is composed of a number of foil strips, extends along the length of the shell. These strips press up against the ID of the shell and effectively seal off the upper half of the shell from the lower half, as illustrated by picture. Unfortunately, the first time the shell is pulled for maintenance, these foil strips are wrecked. Also, unless great care is taken by maintenance personnel when installing the new or replacement longitudinal baffle sealing strips, the heat transfer efficiency of the exchanger will be greatly reduced after it is returned to service. As a result of this deficiency, most operating companies severely restrict the use of 2-pass shell-side heat exchangers. Double pipe exchangers. Also called hairpin exchangers, the double pipe heat exchanger, as shown in picture, is the simplest of all types we have discussed. It is nothing more than two concentric pipes. The inner pipe might be 2-inch diameter and the outer pipe 3 inches. Double pipe exchangers are true countercurrent flow heat exchangers. They are rugged and are reasonably cleanable. Moreover, they are not subject to bypassing. The only problem with them is cost per square foot of heat transfer surface area. A single pipe or tube simply cannot have much area, typically 100 to 300 square feet. Exchangers of less than a few hundred square feet can be economically designed in a hairpin configuration. Larger exchangers are, for economic factors, shell and tube types. Fin tubes. You may have seen bundles constructed with serrated, or very small, fins covering the exterior of the tubes. These are called low-fin tube bundles. These fins increase the outside surface area of the tubes by a factor of 2.5. However, this does not mean that the heat transfer efficiency of the exchanger will increase by 250%. Two factors curtail this improvement. 1. Let's assume that the controlling resistance to heat transfer is inside the tube. It does not matter whether this resistance is due to fouling, high viscosity, or low flow. The heat flow must still pass through the smaller surface area inside the tube. The smaller area acts as a choke point that restricts heat flow. Let's assume that 90% of the resistance to heat transfer is inside and 10% outside the tubes. The overall increase in the heat transfer capacity of the exchanger would, at best, be roughly 15%. 2. Actually, retrofitting a tube bundle with low-fin tubes often reduces heat transfer capacity. This happens when the controlling resistance to heat transfer is shell-side fouling. The fouling deposits get trapped between the tiny fins. This acts as an insulator between the shell-side fluid and the surface of the tubes. In severe shell-side fouling services, I have replaced fin tubes with bare tubes and doubled the heat transfer duty on the exchanger. In summary, low-fin tubes may be used to advantage only when the controlling resistance to heat transfer is the shell-side fluid itself. Heat transfer resistance. The resistances of electric resistors arranged in series may be added to obtain the overall circuit resistance. This concept also applies for a heat exchanger. The following 5 resistances to heat transfer are added together to obtain the total resistance to heat transfer. The tube side fluid. The fouling deposit inside the tubes. The metal wall of the tube. The fouling deposit around the outside of the tube. The shell side fluid. The sum of these 5 factors is called the overall resistance to heat transfer. The reciprocal of the overall resistance is termed U, the overall heat transfer coefficient. Importance of shell-side cross-flow. Shell-side flow should be mostly at right angles or perpendicular to the tubes. Unavoidably, as the fluid flows from the inlet nozzle to the outlet nozzle, there is some component of flow parallel to the tubes. The bigger the tube support baffle spacing, the greater the component of the flow parallel to the tubes. A larger baffle cut also increases the component of the flow parallel to the tubes. Thus, to promote perpendicular flow to the tubes or cross-flow, velocity baffle spacing should be about 20 to 30% of the bundle diameter. The baffle cut should be about 25 to 35% of the bundle diameter. By baffle cut, I mean the cutout section of the round baffle. Reducing the baffle spacing and the baffle cut increases the shell side pressure drop. But that's the price we must pay for improved heat transfer rates. I've read about the importance of shell side cross-flow in heat exchanger design books. Higher cross-flow velocities reduce film resistance and promote increased heat transfer rates. Recently, an engineer had a dramatic personal experience to support this engineering principle. A refinery had a debutanizer reboiler with an observed heat transfer coefficient of 25 BTU per hour per square feet per degree F. The reboiler was a horizontal, thermosiphon, shell and tube exchanger. The heating medium was 400 psi G steam on the tube side. Except for a short length of the tubes, the shell side flow was parallel to the tubes. He designed a new bundle, using the existing shell and nozzles, with new tube support baffles. He mostly eliminated the parallel component of shell side flow. The observed heat transfer coefficient improved to 80 BTU per hour per square feet per degree F. The increased thermosiphon driving force resulting from the larger reboiler duty and vapor generation rate offset the increased pressure drop caused by the new baffles. This kept the circulation rate through the shell constant. Anytime he found that basic engineering principles actually apply in practice, he surprised. He hoped for the best, but planned for the worst. His fear of failure was a basic ingredient in good engineering design. Detecting tube leaks. On stream, engineer was recently working a job at a refinery. The pump-around trim cooler steam generator for the fractionator was thought to be leaking water into the pump-around return hot gas oil flow. To verify the leak, he proceeded as follows. Step 1, on the gas oil side of the pump-around, he partially closed the outlet valve. This forced the upstream control valve to open. Step 2, on the steam side, he reduced the steam generator pressure by partially bypassing the downstream superheater coil. These steps reduced the steam generator pressure from 170 to 150 psi and increased the pump-around gas oil inlet pressure from 140 to 160 psi. He then checked the blowdown drain on the steam generator and found it to be contaminated with the greenish gas oil. This proved that the steam generator was indeed leaking. Incidentally, there were no tube leaks. The leaks were where the tubes were rolled into the tube sheet. These are called roll leaks. There are a wide range of other techniques used to determine, without taking a heat exchanger offline, that the exchanger tubes are leaking. For a hydrotreater feed effluent exchanger, inject dye into the feed. This dye is used in refineries to identify products for sale. Add the dye at its normal concentration as used for product sales. The dye will be destroyed in the hydrotreater reactor. But, if there is a tube leak in the feed effluent exchanger, the hydrotreated feed will still be colored. For a steam turbine and vacuum surface condenser, check for dissolved oxygen in the steam condensate. The oxygen would come from cooling water leaking into the shell side. For amine regenerator reboilers, we used a commercially available leak detector kit. Sulfur hexafluoride was injected into the reboiler steam and the reboiler vapor outlet was then monitored for SF6. The detector is sensitive to 1 ppb billion. The commercially available unit I'm familiar with is sold under the trademark of FluorTracer Analyzer. Both the analyzer and ASF6 dispenser are needed. You can also use this technique to detect heat exchanger leaks. You can use the ordinary air conditioner Freon, which is available in most refineries, and an $800 Freon leak detector kit you can purchase from my neighborhood air conditioner supply store. It's really the same as the SF6 technique. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.